Alright, so now I'm going to derive the heat diffusion equation for cylindrical coordinates. So what I have drawn here is a sliver of a cylinder on a Cartesian coordinate plane. So the sliver has dimensions of r d theta, this is dr, and then dz. So the differential volume for this is r d theta dr dz, and the general energy balance equation is the rate of energy stored is equal to the rate of heat net plus the rate of energy generated. So the equation for energy stored is density times heat capacity times partial derivative of temperature over time times the differential volume, which is r d theta dr dz, and the equation for energy stored is or generated is q dot times r, the differential volume. Alright, and QNet has three different equations for the three different planes that heat is going to be going through, which are QZ, QR, and Q theta. So the first one, QZ, let me first draw this in 3D. Alright, so the first plane that we're going to be going through is this plane. So I'm going to highlight this to stay organized. So the heat is flowing through the bottom, up through the bottom, and out through the top. Oh, excuse me. And we're going to label this as QZ, and this is going to be QC plus DC, because like I said earlier, this length is DC. So QR net is equal to QR minus QR plus DC, and QR plus DC is equal to QR plus the gradient Q through R times dz. And we put this into this equation, and we get QR minus QR plus gradient. And these cancel out. So then that gives us negative gradient over R, the heat over R, gradient of heat through R, dz. And then that gives us, then we use Fourier's law. I don't think I'm spelling that right, don't judge me. And that gives us partial derivative over the partial derivative of R times negative K times area times the partial derivative of temperature over R dz. Alright, so then the negatives cancel out. And area for this is dr times r d theta. Do r d theta first. Alright, so then that gives us I'm going to take this out. Because then that conveniently gives us differential volume. And we can later take that out. I don't know why I'm writing R. It's Z. All of these are Z. Because I just defined it as Z earlier. I'm going to fix that really quick. Here we go. Okay. So now we're going to calculate for R. Alright. So R is going in through this way, out through this way. So we're doing this, calculating for this plane. I'm going to highlight that just to help me stay organized. So we're going to call this position QR and this one QR plus dr because this distance is dr. Like I said earlier. Okay, so QR net QR net is equal to QR minus QR dr. And QR plus dr is equal to QR plus Q partial derivative of Q over R dr. Then you plug that into this equation like before. So then that gives you QR and these cancel out. So then that gives you negative Q over R dr. And then Fourier's law again. So then that gives you that, and the negatives cancel out, and area for this one is R d theta times dr, or I mean dz. And this simplifies to this. You can simplify it. Just write it like this to stay consistent. And now, finally, we are going to calculate Q theta. Hopefully that wasn't in the way the whole time. So now we're going to calculate Q theta, like I said, and that goes through this plane and out this side. So we're going to call this Q theta, and then this side Q theta plus d theta. Alright, so like before, Q theta net is equal to Q theta minus Q theta plus d theta, and dq theta plus d theta is equal to Q theta plus partial derivative over theta times d theta Then you sub that in here, and you basically get Q theta minus Q theta plus the d theta, and these cancel out. So you get negative and Fourier's law again, so you get and then the negatives cancel out. So, okay, and then the area for this is, oh, I forgot to write the d theta. dr dz over partial derivative of temperature, r partial derivative of theta, d theta, and then this simplifies to k dr, oh, sorry. Pull that out from underneath the partial derivative. Alright, so now we join all the equations. So start with this one, move that down here. Add all of these up, then add energy generated. Sorry, I was just rudely interrupted. So what I was saying was I was combining all the equations. So like the energy stored versus the net heat rate, and the net energy generated into one equation. Then I'm gonna cancel out all these beautifully, and then divide by delta CP, and then I'll get heat diffusivity And there we go. That is the heat diffusion equation for a cylindrical object. Alright, so for this problem, I'm going to simplify the differential heat diffusion equation for a steady state with no generation and heat flow, and find the equivalent thermal resistance. So let's first start with the heat diffusion equation for a cylindrical object, which is gradient of temperature over time. This is equal to thermal diffusivity of 1 over R times the derivative of derivative over R times R times the gradient of temperature over R. And we're leaving all that, the rest of the stuff out. So for steady state, this is equal to 0. And then you also cancel out heat diffusivity. So that leaves you 1 over R dr, or d over dr times R dt dr. And then you cancel out these. So then that gives you R over dt dr is equal to C. And now this is a separable equation, so you do dt equals C over R dr. And then we integrate this from T1 to T2, and then R1 to R2. So then that gives us delta T is equal to C natural log R2 over R1. So then C is equal to the natural log R2 over R1, or delta T over the natural log R2 over R1. So now we'll think of the voltage is equal to IR. Voltage is equal to delta T. I is equal to the heat flow, and then we're finding R, what R is. So think of Fourier's law, which is QR negative K dt over dr. So now we have to think of it as the cylindrical object. Oop. R1 to R2. Excuse me. So we have to do this for any area. So how we would write Fourier's law for this would be Q R is equal to negative K times the area, and the area of a circle is 2 by R H, which is the height. and then dt over dr. Alright, so now we are going to write it as, so we're gonna write this as 2 by RH, and we know what dTdr is for C. So it's C over, so this is C over R. And now we write R2 over R1. The R cancel out. So now we want to get this equation into this form. So it's going to be T is equal to Q. Times and we cancel all the negative because we know that heat flow goes from high temperature to low temperature. So this represents R.